Hi. So, we have discussed so far the importance of inorganic elements in biological system and also how those elements are being selected out of so many elements present in the periodic table. Although the metal ions are present in extremely small quantities and surrounded by a huge protein chains, the biological activity are performed only at the metal centers, which clearly justify the crucial roles played by the metal ions. Cobalt is an essential trace element in both prokaryote and eukaryotes. Nevertheless, it occurs less frequently in metalloproteins than other transition metals. This low occurrence appears to be due to the metal's low abundance in nature. Today we will be talking about cobalt metal in biology. You can see that coenzyme B12 is an enzyme containing cobalt. Enzymes are biological catalysts that speed up chemical reaction by lowering the activation energy of the reaction. Enzymes are generally made up of protein and non-protein parts as shown over here. Protein part is called apoenzyme and non-protein part is called cofactor. Non-protein part can be divided into two types again based on their chemical nature. Organic cofactor like NAD, FAD, etc. are called coenzymes. Cofactor can also be metal ions like cobalt, iron, zinc, etc. As you can see here, this apoenzyme, which is basically high molecular mass, mostly protein, it determines selectivity and the rate of the reaction. Cofactor is low molecular mass, it determines the type of reaction, and when we combine both apoenzyme and cofactor, it gives rise to holoenzyme, which is actually the complete enzyme with full functional behavior. This is plot of coenzyme B12 dependent enzyme, and as you can see that coenzyme B12 is a medium sized molecule with a molecular mass of about 1350 Dalton, which exhibits its characteristic specificity and high reactivity only in combination with corresponding apoenzyme. Now, there are several enzymes having this coenzyme B12 and some of them are listed here. You see the large number of cobalt containing enzymes, synthase, transferase, reductase, mutase, lots of enzymes are present. Now, the benefits with vitamin B12, general well-being of the body, particularly boosts energy level, it takes care of the brain and nervous system, good for the digestive system. It also prevents us from disease such as protects against certain cancers, protects against heart disease, helps prevent Alzheimer's disease. It also responsible for some health and beauty, promotes healthy hair, keeps skin healthy, protects nails, lots of things which actually are controlled by vitamin B12. And you can see here lots of good food having vitamin B12. There are certain fish items, meat items, eggs, a lot of other cheese which are having large amount of vitamin B12. Symptoms of having vitamin B12 deficiency in humans. You can have headache, you can have eye problem, you can have pernicious anemia as reflected in the tongue because of vitamin B12 deficiency in our body. And if you do not have sufficient vitamin B12, if you go to the doctor, doctor will prescribe various medicines to supplement the deficiency of B12. Some of these medicines are shown over here. Now, coming back to this coenzyme B12, and as you can see this R, once you change this R, the name also changes. For example, when R is CH3, it is called methylcobalamin. R is cyanide, it is actually cyanocobalamin, which is vitamin B12. R is OH, hydroxycobalamin. R is H2O, aquacobalamin. R is adenosyl. You can see this is adenosyl cobalamin. This is the R value, which is actually a cofactor in the native enzyme. This fifth position, this axial ligand, it is dimethyl benzimidazole unit, which is very peculiar. It only present in vitamin B12. No other enzyme have this axial ligand. As you can see that this macrocycle which is present in the coenzyme B12 is a very peculiar, is called chorin. So, I have actually compared here chorin and a popular macrocycle called porphyrin, which you have seen in so many enzymatic systems. For example, cytochrome P450, catalase, peroxidase. Indeed, our hemoglobin, myoglobin all have this porphyrin ring, and this chorin and porphyrin, if you look at their difference, you see that chorin is highly reduced, highly flexible because it is saturated, and the ring size is much smaller. In contrast, porphyrins are highly conjugated and flat molecules, and of course, it is a rigid because it is due to a extended conjugation, and the cavity size also is larger than the chorin. So, this flexibility of the chorin rings actually allows the change in conformation, which indeed is necessary for its reactivity. This is coenzyme, and this complicated molecule was first structurally characterized by Dorothy Hodgkin, and she got Nobel Prize because of that in 1964. Please note that this is the first molecule where cobalt carbon bond was established. People at that time there was no evidence of such bond, and this is the X structure which leads to Hodgkin a Nobel Prize. You see that cobalt carbon bond, and then this the X-ray structure of this coenzyme B12 is shown over here, and now you know exactly what is in fifth position, what is sixth position, how the rings looks like, what is the distance, angle, all details you can see from the X-ray structure. And this complicated molecule chorin, which is having 9 chiral centers, has been then realized after looking at this X-ray structure. And also she did some of this derivative, one of such derivatives is shown over here, where this axial ligand are chloride and cyanide, and so it is now known, well established, that what is the X-ray structure of coenzyme B12. Indeed, it is such an important molecule. 4 Nobel Prizes related to coenzyme vitamin B12. 1934, Whipple, Minot and Murphy first got this Nobel Prize, on this topic because of the discovery of anti-pernicious anemia factor, now called vitamin B12. 1964, Dorothy Hartkin from Oxford got the Nobel Prize, and this is because of the X-ray structure of these important biomolecules. 1965, Woodward got this Nobel Prize for its outstanding achievements in the art of organic synthesis. Is such a complicated molecule, he could able to synthesize this. 1981, Fukui and Hofmann got also Nobel Prize due to quantum mechanical studies of chemical reactivity. You all familiar with this Woodward-Hofmann rule, and this is based on this coenzyme B12 they have established, and now it is very popular rule for pericyclic reactions. Now, coming back to coenzyme B12, as you can see that this is the only organometallic cofactor known in biological system, and this is also only vitamin having a metal ion, and this is very important for our life. The question is that why nature selected cobalt out of so many elements in the periodic table. Please note that cobalt is only metal where cobalt 3, cobalt 2 and cobalt 1 are stable in aqueous medium, and they are easily interconvertible with each other. No other metal can have this kind of behavior. Say for example, if you take copper, say copper 3 is highly oxidizing. If you take iron, iron 1 is very difficult to get its stability in presence of oxygen. Now, core-in macrocycle also is necessary because you see that cobalt 1 porphyrin is not that stable in under oxygen. Okay. So, but core-in, all these 3 oxidation states are achievable, they are very stable in aqueous medium and easily interconvertible to one another, and we will see that this is why nature utilized cobalt in its macrocycle core. So, again coming back this cobalt 3, which is a D6 ion basically, it converts to cobalt 2 after 1 electron addition, and then it becomes cobalt 1. So, D6, D7, D8, and D8 is, as you know, that it is you can have oxidative addition, D6 you can have reductive elimination converting to D8. So, all these things you can play with that, and also is a cobalt 2, it is a D7 ion, and this one unpaired electron is in dz square orbital as shown over here. This is called radical scavenger, is a radical basically in character, and cobalt 1 this dz square orbital contains 2 electron, although they are paired. As I have already said that coenzyme B12 catalyzes lots of chemical reactions, and the specificity and reactivity depends on the proteins around the coenzyme. Now, the basic chemical transformation that this coenzyme B12 catalyze is the migration of group. As you can see that this X comes to want to shift, this comes over here and proton goes over here, this migration of the group. And the next example you see that the CH2 group has been migrated and converted to the methyl. This is what is happening in methyl malonyl coenzyme A mutase. So, basically groups are getting migrated from one carbon to another carbon in these reactions. And there are some more isomerase reactions through 1,2 shifts, and you can see that this even amino group also getting migrated to another carbon. It is also deamination reactions where it liberates NH3 groups, and diol dehydrase also, where you can see that 1,2 shift, and after that the elimination of water leads to an aldehyde group. Now, all this chemical transformation is believed to go through via a radical pathway. So, I will now show how coenzyme B12 catalyze chemical reaction. So, as you can see, this ADO B12 first undergo a homolytic cleavage. Cobalt carbon bond gets undergo a cleavage and forming that ADO CH2 radical plus reduced B12, that means which is actually cobalt 2. Now, this radical actually responsible for all these transformations which are happening. I will show how this radical is responsible for that. Now, this is an overall reaction which is shown over here. As you can see that this the X group migrates from C1 to C2 unit, and this is the product. Now, how this migration is possible using this radical ion. Now, this adenosine radical actually abstract the proton, forming a C2 radical, and this C2 radical undergo a rearrangement and this radical comes from C2 to C1, it is migrate from C2 to C1, and then X comes from C1 to C2, and this radical abstract another proton from adenosine CH3, and then it gives this product. So, as you can see that formation of the radical is very crucial. Can this radical you can generate just by cleaving CC bond as well? Yes, you can. However, if you look at this bond energy of CC bond, it is 80 to 90 kcal per mole, whereas if you use cobalt, you reduce dramatically the bond energy, and it is only 26 kcal per mole. So, just light or thermally you can cleave this cobalt carbon bond and form this radical species, and thereby you can do miracle in your catalytic reactions. I have discussed coenzyme B12 dependent enzymes today and highlighted their role in catalyzing a large variety of chemical transformations in biology. You also have seen and enjoyed the beauty of nature's design in the B12 and the selection of cobalt and the chlorine macrocycle therein. The importance of cobalt carbon bond has been highlighted here, which indeed responsible for a large number of chemical transformations in biology. I do hope you all enjoy looking at the role of inorganic elements in biology. In my next few lectures, I will show you the beauty of nature's design in controlling the chemical processes that are responsible for our survival in this earth. Thank you.